Hello, today we're going to go over AP Chemistry Chapter 6, Sections 2 to 4, and it is on thermochemistry. So we have two basic types of energy. Energy is just the capacity to do work, and work is a force applied over a distance. So, for example, if you push a box across the floor, you're doing work. You're applying a force over a specific distance. Okay, so that is the definition of energy, the ability to do work. And there's two types. So we have kinetic energy, which is the energy of motion, and we have potential, which is due to the position of the objects. So kinetic energy, you guys know the equation. Kinetic energy is going to be 1/2 mv squared. So we have the mass of our particle in chemistry, this is the mass, and the velocity squared. Okay, and we know that at the same temperature, they have the same average kinetic energy no matter what the particle is. We just talked about that. Thermal energy is a type of kinetic energy. Thermal energy has to do with the temperature of the object, so how fast the particles are moving. And over here, potential energy is related to chemical energy in chemistry because it's the position of the electrons and the protons that holds all of these atoms together. So in biology, you guys learned about ATP and other molecules like that storing energy. So what's really going on is you have the negative electrons on one atom and the positive protons on another atom, and there's a force because these are opposite charges that pulls them together. Okay, this is Coulomb's law that we're going to learn a lot about later, and we call it the Coulombic force. It just says that these opposite charges are going to pull towards each other, so there's going to be a force there, and this force is what creates the potential energy. So this potential energy of our molecules comes from the electrons and the protons being attracted to each other, or repelled. If you have electrons and electrons, they're going to repel, and you have the opposite. The force would be pushing them away from each other. All right, so energy conservation and transfer. The law of conservation of energy says that energy cannot be created or destroyed. We've learned that one probably since 8th grade. It can be transferred from one object to another, so we can transfer heat into and out of a system. We're going to talk about that. And it can change different forms. So like in a roller coaster, you have potential energy due to gravity, and then that turns into kinetic energy when the roller coaster goes down the hill, right? So energy can be transformed into different types, and it can be transferred between objects. So here is our definition of the system. The system is just whatever is being studied. So in this case, I made a beaker, our system. Sometimes it's a test tube. That's the system. It's just whatever we are specifically studying. Sometimes it's very specific, like not only is it's not the beaker, but let's say we're doing the dissolution of salt. The salt might actually be our system. So we're going to see, does the salt take in energy or does the salt give off energy? That would be our system. So we have to define what it is we're studying, okay? And the surroundings is basically everything else. So in this example that I was just talking about, the surroundings would actually be the H2O, the little molecules that are around the salt. In the picture over here, these surroundings would be everything outside of my beaker. Okay, so I'm studying everything inside the beaker versus outside the beaker in this example in the slides. And if heat goes in, we know that as endothermic, you guys know that. But the energy is going to be positive. So think of it as like a bank account. So if you are the system and you have money coming in, the change in energy is going to be positive. This should be delta E. The change is positive. If you're giving off money, if you're transferring money to other places, then the change is going to be negative. Your energy is going to go down, or your balance. Units of energy, because kinetic energy is 1/2 mv squared, we use the units for mass and velocity squared to define the units of energy. So we have kilograms, that's mass. M per second, meters per second, is a velocity, and squared becomes meters squared per second. So this is how we write joules written out in SI units, but we just write J, capital J, and because they're really small, usually it's kilojoules, which is kJ. Okay, so that is the definition of a joule, which is the unit we use for energy in chemistry. And you might also know calories. Calories is more of a biology term, and that's what we use for food when we calculate how much energy is in our food. 1 calorie is equal to exactly 4.184 joules of energy. Okay, so section 3 is on the first law of thermodynamics. Thermodynamics, thermo and dynamic meaning change, just means we're studying how the energy is changing. So energy comes and goes during reactions, and that's what we're studying here. The first law of thermodynamics says that the total energy of the universe is constant. So nothing is being created or destroyed. It's just moving from place to place or object to object. The internal energy of a system is the sum of the kinetic, so the motion, and the potential, so the position energies of all the particles that are in that system. So we're going to talk about the internal energy. So if this was my system, the energy of my little salt molecules would be their motion and their position. So we have positives and negatives in the salt, right? Because it's ionic. All right, so to find delta E, remember that this symbol means change. So this is the change in energy of a reaction. And in the reaction on the, in the reaction on the left over there, we have hydrogen plus oxygen reacting. This is an explosive reaction, right? If you have a balloon filled with hydrogen gas, it reacts explosively with the oxygen and it gives off a ton of heat. Why is that? That's because hydrogen and oxygen have a high internal energy, and water is very stable. You guys know water doesn't want to break down into anything else. That's why it covers most of the earth. So when these form water, okay, this is turning into this. It's kind of like writing the reaction vertically instead of horizontally. So when these turn into this much energy is given off. That's our delta E. Okay, and it comes out. So we would say that for this reaction, the change in energy is negative. Okay, it would be my final energy, which we can make up numbers, but I'm not going to. So this would be the final energy minus the initial energy. And since this is a smaller number, because it's lower on this scale, you're subtracting a bigger number, you're going to get a negative value. Okay, and the opposite of that is true. So if I have the opposite graph, where I am starting with my water at the bottom, water is still, I didn't mean to put that O. Water is still down here because it's still low in energy. And the hydrogen plus the oxygen. So if I'm taking water and breaking it down, I'm going up. From water, you have to put electricity in it in a battery and run the electricity through the water, and it will split into hydrogen and oxygen. I'm adding energy. Okay, I'm adding this much energy. So my delta E, it would be the same value, but now it's positive. Now it's the opposite sign because it's going in. So we called this exothermic because heat came out when I made my water, and we call this endothermic because heat goes in when you break water down. Okay, so we also need to know our MCAT equation for this section. And MCAT is, we have heat. Remember that heat is a Q, and we don't know why. We just have to deal with it, is equal to mass times specific heat times the change in temperature. So this equation is pretty straightforward and simple. Most of the problems involving these are also straightforward and pretty simple. We're given 3 things, we plug them in, and we find the missing thing. The hardest ones involve temperature, and we'll go over one of those later. Okay, so for our example in the book, we find a penny, and it's made out of mostly copper because it was minted before 1982. How much heat is absorbed? We're looking for Q. Okay, we're looking for Q. As it warms from negative degrees Celsius to the temperature of your body, which is 37 degrees Celsius. Assume the penny is pure copper and has a mass of 3.1 grams. So 3.10 grams is my M. So I'm going to plug that in. The specific heat of copper, we have to know what that is. And specific heats you can look up in your textbook or even just online. So it gives it to us. It's 3.85 joules per gram degrees Celsius. That's how many joules you have to add to raise the temperature of 1 gram by 1 degree Celsius. So that's our specific heat. And the temperature change, it goes from -8 all the way to 37. So it has a temperature change of 45 degrees Celsius. Now notice in the gases chapter, we made sure that it was in Kelvin. But in this chapter, you can actually replace Celsius with Kelvin or Kelvin with Celsius, so the temperature doesn't matter as long as they match up. So we want Celsius, and we're good. Okay, and that's it. When I multiply those together, I will get the Q. I will get how much heat is given off. And I'm going to go with your book's answer because you guys know my track record of calculating things. Okay, and we get 53.7 joules of energy. I want you guys to try the for practice 6.2. Okay, which should be very similar. Determine whether I'm looking for what we are looking for. Find the specific heat. So that's what I thought. So in the for practice 6.2, you're actually solving for specific heat. And if I rearrange this equation to solve for CP, I'll get Q, or heat, over mass times the change in temperature. So you're going to use this formula, okay? Or you can use this one and just solve for C for practice. All right, and last, we're going to go over the conceptual connection. So you guys have been working with the natural world your entire lives, so you have some kind of innate sense of the specific heat of water. So let's talk about this question and see if you can come up with the right answer based on what you know. Suppose you are cold weather camping. I don't know if you've been camping in the cold, but it's not very fun. And you decide to heat some objects to bring into your sleeping bag for added warmth. You place a large water jug and a rock of equal mass, so they're the same size, same mass, near the fire. Over time, both the rock and the water jug warm to about 38 degrees Celsius, which is about 100 degrees Fahrenheit. If you could bring only one of them into your sleeping bag, which one would you choose to keep you warmer? Okay, so if you said the water, then I highly agree. And the reason that water would be the smart choice is because it has a specific heat of 4.18 joules per gram degree Celsius, and this is one of the highest specific heats of anything. So rock is going to have a lower specific heat, metal definitely has lower specific heat. So what that means is it holds a lot of joules and the temperature doesn't change very much. Okay, so it takes a long time to heat water up, and it takes a long time for the water to cool back down. So it's going to be holding more heat inside of it. It's going to hold more energy inside of it because of those hydrogen bonds between the waters than the rock would. Okay, hopefully that made sense. And that is it for today. I hope you guys have a wonderful day.